This is Chemistry of Carbon and its Compounds, Part 6. This podcast will talk about the nanoscale, some ideas behind the concept of green chemistry, synthetic reactions, and the understanding of functional groups and the test for specific functional groups. The assessment criteria is pretty wide open. It talks about appreciating the nanoscale and learning a little bit about the nanoscale. It talks about green chemistry. And then it talks about specifically organic compounds, functional groups, and multi step synthesis reactions. Appreciate the nanoscale and know some uses of nanoparticles. Nanotechnology is research and technology and development in the nanometer range, 10 to the minus 9 meters. One of the first advances that allowed us to look at this nanoscale was the scanning tunneling microscope. It's not like a normal microscope. It doesn't see atoms, but it feels them. As a fine tip scans a surface, it records a signal depending on the atoms the tip passes over. If you look at the orange colored picture in the bottom right, you'll see a nanotube. You'll also see a scale there. We're talking about a nanotube that is about 1 times 10 to the minus 9 meters in diameter. And that's a picture of that nanotube made by a scanning tunneling microscope. The discovery of the allotrope of carbon, C60, led to the discovery of a whole new family of structurally similar carbon compounds. They are carbon, but in a way that we have not seen carbon before. And these nanoparticles have and do have significant opportunities for us in our current day. You can see no matter the industry, there is a current use that's being used right now and a potential use that can be used in the future. So, what are these particles? The first is Buckminster fullerene. It's a combination of hexagons and pentagons, much like what a soccer ball would look like. And those are carbon atoms that are on the outside of this Buckminster fullerene or buckyball. Other fullerenes have been found with up to C70, and these have been called other names that refer to Buckminster Fuller. Graphene is a 1 atom thick sheet of carbon atoms. Notice again, they're in hexagonal shapes, and it's remarkably strong for its very low weight. Remember, it's only 1 atom thick. Conducts heat and electricity very well. Nanotubes are graphene rolled into tubes, if you wanted to look at them. And they're a cylindrical nanostructure. They can be used for a variety of purposes, from electrical conductors to use in the human body for stents in the heart to replace veins and artery problems. Green chemistry is the design of processes and products that reduce or eliminate the use of lots of hazardous substances. Green chemistry includes the design of a product, its manufacture, its use, and ultimate disposal. It's also known as sustainable chemistry. The idea here is to solve real-world problems with chemistry, but without the hazardous byproducts. There's a video I'd like to show you now about green chemistry in Canada, which will describe in greater depth the ideas behind green chemistry.
Did you know that 97% of all products and industrial processes require a chemical reaction? But many of those reactions result in huge amounts of waste and toxic byproducts. A revolution is needed, and McGill University is among the world leaders in the revolution called green chemistry.
Chemistry. It's everywhere. It's in what we eat, what we wear, what we buy, and what we breathe. Chemical reactions are involved in just about all aspects of life.
Unlike any other scientific topic that I'm aware of, it impacts on all of us every day. 97% of everything that we touch, that we do, that we work with in our daily lives has had a chemical process associated with it, or is actually a chemical material.
But manufacturing all these products creates an enormous amount of waste. Take, for example, the pharmaceutical industry. For every 1 kilogram of valuable product produced, an average of 25 to 100 kilograms of waste is created, often toxic waste. The purpose of green chemistry is to reinvent manufacturing processes in order to reduce or eliminate waste and toxicity. It's what the makers of ibuprofen did. The second most widely used painkiller in the world is more affordable today thanks to green chemistry. The patent holders reinvented their chemical process in 1993 to make it green.
So the effect has been a substantial increase in the profit margin for these companies. They're much more viable as businesses. The product is out in the market at very reasonable prices, incredibly reasonable prices actually, and green chemistry played a big role in that.
Professor Bruce Lennox, chair of McGill's chemistry department, says there are countless chemical processes that could be made more efficient.
Normally a chemist will take material A, they add it to material B to give C. They take C, they add it to D, they make E. They take E, they add it to F. This can be a series of 10 or 15 before you run out of the alphabet. Every one of these reactions has the potential for only being 50% efficient or even 80%. By the time you're finished a 10 or 15 part series, you now have an efficiency that's maybe 1%. Everything else is waste. Every one of those processes has the opportunity to be improved or greatly improved in terms of its environmental footprint.
Now, as part of the preparation for your end of year test, you will have to identify functional groups from chemical reactions. And you'll have to do this in the organic sense, and you'll also have to be able to identify inorganic compounds based on their reactions. Now, we have done sufficient enough practicals in organic chemistry for you to know a couple of the things, such as the silver mirror test. There are over 14 tests that we will ask you to memorize, and we will provide you information on how to memorize the tests for those functional groups. The last significant topic is synthesis in organic chemistry. How do you make a desired product? We will spend, again, a good deal of time during fourth term, grade 12, to look at over 50 chemical reactions that you have learned in grade 11 and grade 12 Cambridge chemistry. These reactions will give you further ideas on how you might be able to synthesize carbon compounds. Let's look at a short video that describes the steps in organic synthesis.
Nature effortlessly creates really great and complex bioactive molecules. It's no surprise that chemists also make molecules. For the past 100 years, chemists have strived to make bioactive molecules with desirable and interesting properties. Most of the time, these molecules are found to exist in nature, but are generated in such small amounts that in order to get a single usable dose of the molecule, you might have to wipe out an entire species of the organism. This is less than ideal, so chemists from all around the world work independently and collaboratively to design chemical pathways that could lead to the creation of some of these great molecules. This is also known in organic chemistry as a synthetic strategy. First, a chemist starts off with a target molecule, a natural product that is shown to have desirable bioactivities, and usually, through the logic of retrosynthesis, devises a means of generating this natural product. It's no good if a chemist has to use equally scarce chemicals to make a target molecule. So it is very desirable, if not required, to be able to create a synthetic strategy that is derived from simple, commercially available chemicals, also known as a total synthesis. In order to create a successful synthesis, you need to make your synthesis as efficient as possible. Since every step in this chemical synthesis has a particular percent yield, it is important to either reduce the total number of steps or increase the overall percent yield for each step. This process is called optimization and is what synthetic chemists do after they've been able to generate a natural product from simple starting materials. Due to the chiral nature of our biology and the molecules created in nature, chemists have to stay on top of their game and maintain stereo control when creating a molecule with stereoisomers. So if you can isolate a natural product, synthesize it from simple commercially available chemicals, optimize the synthesis, and produce an optically pure stereoisomer, you are participating in one of the coolest things our human brains are capable of: organic synthesis.
Here are some questions to start your thinking. Nanoparticles have a wide open opportunity in science and technology. These two questions ask you to think outside of the box in regards to the use of these nanoparticles. See you later.